Hello everyone, this is Dr. Lennon, and today we're going to talk about the limit comparison test. So we've built up a number of series that we understand how they converge using divergence tests, geometric series, integral test, and things like that. So what the limit comparison test does is it gives us a way to compare series. So if we know one looks something like another, we can compare them using limits. And what that will do is it will allow us to determine their convergence or divergence based on tests we already know. So it's really quite handy, especially if they just look a little bit different based on some kind of terms that we might perceive to be insignificant. So let's go ahead and just write down the theorem and then look at some examples. There's also other comparison tests, but really they're all kind of subsumed by the limit comparison test. A lot of times they're used to motivate them. But I'm kind of going to be skipping over those, so we're just going to look at the limit comparison test, because all the ones that you can do using other comparison tests can be done also by using the limit comparison test. So theorem, this is the limit comparison test. So usually what happens is you're looking at a series and you have some series in mind that you want to compare it to. So with that being said, so let's let one series be the sum of some a sub k's, and another one be a series of some b sub k's with positive terms. And suppose they converge to some limit, so we're going to look at the ratio of them. So let's look at the limit of the terms as k goes to infinity. So let's write it as a to the k over b to the k, and let's say this is some limit capital L. So basically the main case is kind of, so we'll say then, so 1, if your limit is some finite number between 0 and infinity, then however one series behaves, the other one will also behave that way. So then either the series a sub k and one with the b sub k's both converge, or they both diverge. So usually that's the case we're going to see because we have some series in mind that we want to compare it to, and we'll typically want to be comparing it with some series where we understand the behavior of that series. Okay, but there are the two other results. What if L happens to be 0, or if L happens to be infinity? So if L is equal to 0 and the b sub k's converge, then we know the a sub k's must also converge. So if you think about that, we're looking at the limit. So if the limit's going to 0, that means the b sub k's are actually growing faster. So if those are converging, then the a sub k's, since they're all positive, have to be smaller, and they're going to be converging as well. And then, so if L is equal to infinity, we've kind of got the other thing happening. So that means if we know that, say, the bk's diverge, that means the a sub k's are growing even faster, so they're going to have to diverge. So those are all the hypotheses for the theorem. So let's go ahead and just look at a couple of examples. So example, let's say evaluate or determine whether the series converge. So let's look at the first one. So let's say we're going from k equals 1 to infinity of 5k to the 4th minus 2k squared plus 3 over 2k to the 6th minus k plus 5. So what are we doing here? Basically, we know that essentially, if I'm thinking about this, I'm looking at the first term, 5k to the fourth, and the bottom one, 2k to the sixth. And for me, I know that's essentially, if you would look at the ratio of the powers of k there, that would end up being 1 over k squared. So I would say let's compare with the series, let's say, I don't know, k equals 1 to infinity of 1 over k squared, which converges by the p-series test. So we know it converges, and our hope is that this limit will approach some finite number. So then we check the limit. So we look at the limit as k goes to infinity of 5k to the fourth minus 2k squared plus 3 over 2k to the sixth minus k plus 5, and we're dividing by 1 over k squared now, so that's multiplying by the reciprocal, which is k squared over 1, and this limit is in fact by the fact that we only have to look at dominant terms when evaluating limits of rational expressions. Basically, this is going to be the same as 5k to the sixth over 2k to the sixth, and we know that limit will just evaluate to 5 over 2, which is a finite number. And since we know 1 over k squared converges, we know that the series that we're looking at above will also converge. So hence, the series in question converges. So that's it. That's a very straightforward use of the limit comparison test with a series that's determined by a rational expression in closed form. Okay, let's move on to another example. So let's look at the series that is k equals 1 to infinity of the natural log of k over k squared. So again, with this one, the most likely candidate is to compare it to either 1 over k squared or 1 over k, something like that. So let's compare to 1 over k squared. So if we compare to 1 over k squared, again, we're looking at the limit, and you can pretty quickly see that this limit is not going to end up as a finite number, so we're going to rely on one of those other comparisons. Let's see what happens. So we have the limit as k goes to infinity of natural log of k over k squared times the reciprocal of the series we're comparing it to. So we're getting the limit as k goes to infinity of actually just the natural log of k. And we know that goes to infinity. Again, the series we're comparing it to, this is our acting like our b sub k in the theorem, which converges. So if we look back to the theorem, we can ask, does this apply? So if L equals 0 and the sum of bk converges, then the a sub k's converge. So what happened with us? We have the limit, our limit actually turned out to be infinity in this case. So since our b sub k's converge and don't diverge, it does not apply here. So we're going to have to try a different comparison. So that turned out to be inconclusive. So let's try the other thing I suggested. Maybe, so this comparison is inconclusive. So let's look at the compare to the harmonic series, compare to, let's say, k equals 1 to infinity of 1 over k, and we know this diverges. So we're now looking at the limit as k goes to infinity of natural log of k over k squared times k over 1. So this is the limit as k goes to infinity of natural log of k over k. And this goes to 0. You can check that by L'Hopital's rule if you want. So this is going to be the same as the limit. If you take the derivative of the top and the bottom, they're currently both going to infinity. This is 1 over k by L'Hopital's. Which is equal to 0. Well, it turns out this is also going to be inconclusive because our series diverges, it doesn't converge. So this does not give us a notion about whether or not this natural log of k over k squared converges. So this comparison is also inconclusive. Okay, so what do we do then? Well, we have to try to compare it to something else. We try something in between that we know actually converges, right? Remember, this 1 over k series is right on the edge of diverging. Any power bigger of k is going to converge. So let's compare to something slightly bigger. Let's compare to the series k equals 1 to infinity of, let's say, 1 over k to the 3 over 2. Again, which converges by p-series test. So, what does that mean? Well, we have to do the limit comparison one more time. So we get the limit as k goes to infinity of the natural log of k over k squared times k to the 3 over 2 over 1. So now this is actually leaving us with a little bit nicer limit in terms of evaluation because we've now got natural log of k on top, and what do we have on bottom? We've got just we've got k to the 1/2 on bottom. And the reason it's a little bit nicer is because k squared converges, but it was almost too big because it was when we took the derivative, we got something that was still larger and ended up making the limit go to 0. Now let's watch what happens. So again, this is a L'Hopital's rule because natural log of k is going to infinity, and so is k to the 1/2. So we can apply L'Hopital's rule here. So we get the limit as k goes to infinity of 1 over k times 1/2 times k to the negative 1/2. Okay. Doing the, oh, excuse me, that k to the 1/2 needs to be in the bottom. Sorry, it's 1 over k times 1 over 1/2 k to the minus 1/2. So flipping the fractions over and simplifying, what do we get? We end up getting a 2 on top, and then the k to the negative 1/2 would be on top, and so that would actually be 2 over the square root of k, which is going to go to 0 because the bottom is going to infinity. So let's think about what happened here. We ended up getting the fact that the series that we're looking at converges, but the problem is, so it went to 0. When we compared it to k, it also went to 0. But the problem with the harmonic series, it diverged, so it was inconclusive. But now 1 over k to the 3/2 actually converges. It doesn't diverge. So this is going to leave us in the camp of number 2. L equals 0. That's our limit. The series we looked at converged, so that's the 1 over k to the 3/2. So the series that we're looking at also converges. So therefore, by conclusion, number 2 of the limit comparison test, the series natural log of k over k squared diverges, or converges, sorry, converges. So that's pretty much it for the limit comparison test. Again, usually the comparisons are obvious. This second example that we looked at was a little more difficult, but again, a lot of times you're just comparing them to series you know. So, and you know, a lot of times it'll come back to evaluating some limit techniques. As you saw, some L'Hopital's rule came up and things like that. But super useful theorem, used in conjunction with all of our other tests, is a really, really nice tool for finding the conversions and diversions of series. So this is Dr. Lennon signing off.